Hello everyone, I'm Mr. McBrien. This is SPH3U, Kinetic Energy. So the Ontario curriculum wants us to understand the concept of kinetic energy, be able to solve problems between power, energy, and time, and conduct inquiries involving the relationship between power and work. And that's what we'll do today. So today we're going to talk about the energy contained in a moving object, learn how to calculate kinetic energy, and then do a little inquiry looking at kinetic energy in a sprinting high school student, not a sprinting high school teacher. And we're going to calculate the calories burned in a sprint. Okay, so let's back up for a second and remember last unit. Force equals mass times acceleration. When a force is applied to accelerate an object from v1 to v2, the work done on the object then can be written as force times delta d, but by substituting in mass times acceleration for force, we get work equals mass times acceleration times delta d. Let's back up even further and talk about kinematics. Acceleration equals v2 minus v1 over delta t, and delta d equals our average speed times delta t. So 1/2 v1 plus v2 over delta t. The only constraint here, of course, is constant acceleration. Well, what we can do is go back to our mass times acceleration times delta d expression that we just derived and substitute in acceleration, v2 minus v1 over delta t, and delta d, getting 1/2 v1 plus v2 delta t. And now here's where we do some hardcore algebra. So we can take the delta t, cancel it out. So delta t on the bottom, delta t on the top, and cancel it out. We can move the 1/2 over to the left-hand side. And then we're left with 1/2 m times v2 minus v1 times v1 plus v2. And our algebra allows us to simplify that half of the expression to v2 squared minus v1 squared. Now, it may take you a few seconds to go through the math of that and convince yourself of it. Or maybe you can just trust me that our work equals 1/2 times the mass times v2 squared minus v1 squared. So back to kinetic energy. Since that's the work done to increase the speed of the object, the energy that's increased is the object's kinetic energy, Ek. So kinetic energy, change in kinetic energy, is 1/2 mv squared minus 1/2 mv1 squared. And if we substitute in 0 for v1 squared, or 0 for v1, we get our kinetic energy at any given time being the energy that it took to go from 0 to v2, or the kinetic energy of a given object in motion, based on the law of conservation of energy. So, in just a few seconds, we've walked through some of the meat of the previous two units to get to kinetic energy equals 1/2 mv squared. Okay, so let's apply it to an example. A car of mass 1,500 kilograms is traveling at a speed of 24 meters per second. Calculate the kinetic energy. Well, pretty straightforward. We know the mass, we know the velocity, and we know our expression now for kinetic energy, 1/2 mv squared. And we can quickly calculate out and get 4.3 times 10 to the 5 joules. Note that that should be an exponent. Okay, our second example is a little more complicated. An object of mass 5 kilograms is traveling at a speed of 4 meters per second, and we do 27 joules of work to increase the speed. What's its final speed? So in this case it's a little more complicated. What we need to do is say that the kinetic energy is equal to the initial kinetic energy plus the work done. Law of conservation of energy, of course. And so we can calculate the initial kinetic energy and add 27 joules. Punching that into our calculator gives us a kinetic energy final of 67 joules. Now from there we can do simple algebra using kinetic energy equals 1/2 mv squared to calculate for V. V equals the square root of 2 times Ek over mass. And substituting in, our new velocity is 5.2 meters per second. So we've cut this pretty short today in order to make time for the sprinting activity. Feel free to do that at home if you wish, just don't do it in traffic. And please do the questions noted from the textbook. So today we calculated kinetic energy from speed and derived the expressions needed to do so. We worked out how to get speed from the work done. We figured out how fast we can run 10 meters and figured out how many calories this burns. Thanks very much for your time. Have a great night.